In this video, we're going to talk about the real numbers and do a short classification system of the number sets inside the real numbers. So when we talk about numbers, we want to be all on the same page and have the same language. So we're going to talk about numbers, and I want to make sure every person knows what we're talking about. So if we refer to something called counting numbers or natural numbers, those are numbers like 1, 2, 3, 4, 5, and so on and so forth. Numbers that you first learn and start to count. So think about when you were uh, when you were first in school or first learned to count. You started counting 1, 2, 3, 4, 5, and you can keep going up and up and up forever. So like 4,391 is a natural number. The whole numbers are the natural numbers along with the number 0. So counting numbers start at 1, whole numbers start at 0. The other common type of numbers that we'll discuss are the integers. The integers are all of the whole numbers and then the negative values of those whole numbers. By the way, we don't need a -0 because -0 is 0. But all of the natural numbers along with their negatives, along with 0. 0 is neither positive nor negative. And so the integers go forever in both directions. They go forever in the negative direction and forever in the positive direction. Now, two other common sets of numbers that we will refer to are the rational numbers and the irrational numbers. The rational numbers consist of all numbers that can be written as A over B, where A and B are integers, and the denominator, which is B, is not 0. We can recognize rational numbers when they're written as A divided by B fairly easily, but we can also recognize rational numbers based on their decimal expansions. If I look at the decimal expansion of a rational number, it is going to either stop after a certain number or it's going to have a repeating pattern. On the other hand, irrational numbers cannot be written as A over B, where A and B are integers with denominator not 0. And irrational numbers have decimal expansions that go on forever and don't have a repeating pattern. So rational numbers can be written as A over B, where A and B are integers. Irrationals cannot be written that way. Now, the real numbers are just the rational numbers and the irrational numbers combined. So all real numbers are numbers which can be measured in a specific direction, and those are the rational numbers and the irrational numbers combined. You may say, well, what about the integers? Well, in fact, the integers are in fact rational numbers because 2 divided by 1 is 2 and 3 divided by 1 is 2. Since 3 and 1 are integers, I can write every integer as that number divided by 1. You can also write that an integer as like 3 is 6 over 2 or some other improper fraction. So all integers are rational numbers. Now, oftentimes we have diagrams to easily see what types of numbers are what. I've drawn this diagram. It's a pretty crude diagram where we have a bunch of numerical values. So the natural numbers are the numbers 1, 2, 3, 4, and 5. They take up this little space. If you add 0 into that, you get the whole numbers. If you add 0 and the positive uh, integers and then plus the negative integers, then you get the integers. Now the integers plus numbers like 4/5 or 7/3 or 4/91 or -4/91 or -91/4, all of those consist of rational numbers. So the rational numbers covers all of those. And then the irrational numbers covers numbers which don't have a nice decimal expansion. Common irrational numbers are things like pi. There's a number e that we'll talk about later in the class. Square root of 2 is an irrational number. Square root of 5 is an irrational number. This is the fifth root of 7. That's an irrational number as well. And then together, all of the rational numbers plus all of the irrational numbers combined make up the real numbers. Now, for this point in the class, we're just talking about real numbers. Later on, though, we'll talk about complex numbers, and we'll see that the real numbers are just a part of the complex numbers. So all of these are real numbers. That's just one part of the complex numbers. Now, we call things real numbers because we can plot those in a real sense. We can measure those. We can plot them on a number line, for instance, or we could understand their length. So any real number can be measured and put on what we call the real number line. At some place on this real number line is our value of 0. I put that right here. And then as you move to the right on the number line, you're moving in a positive direction. As you move to the left, you're moving in a negative direction. I do want to emphasize where you put 0 is arbitrary. I put it right here, and you can see that it's slightly skewed to the left. So there's more positive numbers that are visible on this particular number line than there are negative numbers that are visible on this particular number line. If, however, you'd have put the 0 over here and then started counting, you could have done that as well. And you'd have a lot more positive numbers. If you put the number 0 over here, then you'd have more negative numbers on the real number line, at least in this visual. But specifically, the real number line goes forever to the right, forever to the left. Usually we draw it horizontally. You could draw it vertically as well. So let's describe some of these numbers and then plot them on a number line. So let's start with the number 5. Here we have 5. That is a natural number or a counting number. It is also a whole number. It is also an integer. It is also a rational number, and it's also a real number. We'll see later that's also complex, but so it's natural number, a whole number, an integer, a rational number, and a real number. So it's all of those things. If I'm trying to plot it on a number line, I'm going to put my label of 0. I can technically put it anywhere I want, but I'll put it right here. I'll label it in blue. And then I move over, I'm assuming this is 1, 2, 3, 4, 5. A lot of times we put just a dot to indicate where it is. So there is the number 5. And that's it. That's all we have to do. Now let's take a look at -3/5. This is not a natural number because it's not a counting number. It's not a whole number. It's also not an integer. It is a rational number, and it is also a real number. So -3/5 is rational because it can be written as a over b, where a and b are integers. It can be written as -3 divided by 5, and it is a real number. Now, there's a lot of different ways to deal with this. Sometimes people will put a 0 right in the middle. Let's say we're right there. And then they'll call this a 1 and this a -1. And then -3/5 would go to the left 3/5 of a unit to the left of 0. So that's one way to go about that. Another way to go about that is assume that this is 1, so that each jump is actually a jump of 3/5, or excuse me, it's of 1/5. And then as we move to the left, 1, 2, 3, 4, 5, we'll assume that's -1. And then -3/5 is easy to see now. I move 3 1/5 units to the left. And that would be my point of -3/5 right there. So depending on how I make the labels on my number line, that'll determine how I can plot the number. Let's look at -9. Since it's a negative number, it is not a counting number. It is also not a whole number. It is an integer. It is also a rational number because I can write it as -9 over 1 if I like. And it is also a real number. Any rational number is a real number. If I'm trying to plot -9 on my number line, I may put my 0 value over here just so it's easier to count, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 units to the left. Whoops. Would put me right here. And so that looks like a -9 to me. What about pi? Well, pi is approximately 3.14159. Pi is not a whole number, not an integer, and not rational. Pi is an irrational number because if you look at the decimal expansion of pi, let me say it this way. It's 3.14159, but it keeps going and going and going, and it doesn't have a repeating pattern. So it's irrational, but we know all irrational numbers are also real numbers. So it's irrational and real. If you're going to plot this on a number line, what I would do probably is I'd plot out where 0 is, and then I'll use each tick mark as a 1. Since it's a little bit above 3, pi is somewhere right here, somewhere in that neighborhood. So that is where pi is at. And that's it. That's the whole thing. Plotting points on a number line, we can start with 0 anywhere we want. We can classify numerical values. We can also plot them on a number line. Let's do one more example. Let's look at example 2. We'll describe the numbers and plot these on a number line. Root 7, that is square root of 7, negative 10.6, 9.3 repeating. That line over the 3 means that it just goes 3, 3, 3, 3 forever. And then 42. So if you want to push pause on this video, state what types of numbers each of these are, and then plot them on a number line. I'll show you how that's done in a couple of seconds. So let's take a look at doing that for the square root of 7. We're going to decide what type of number this is. By the way, square root of 7 is equal to about 2.645751311. And if you went out further and further, you'd see that this decimal expansion does not have a repeating pattern. So there's not a repeating pattern, and it has a decimal expansion. So what we can say is that it's not a natural number. Let's cross that one off. Not a whole number. Not an integer. And it's not rational because we don't have a repeating pattern. It is irrational because I can plot it on the number line. And it is a real number because I can plot it on the number line. So square root of 7 is irrational and real. What about negative 10.6? Well, this is a decimal that ends. And you can rewrite this in a number of ways, but one easy way to rewrite this is negative 106 divided by 100. And so we can see that it's integer divided by integer. Therefore, while it's not natural because it has a decimal has something after the decimal, it's not whole, it's not an integer, it is rational because it can be written this way. It also can be written other ways as well. That's not the simplest form. So this is a rational number that is also a real number. By the way, again, this can be written in other ways as well, like negative 53 over 50. Now, if we're going to plot these on the number line, then what I'll do is I'll just call one of these spots 0. We'll call that spot 0. and I got to move over about 2.645 units. So 1, 2, and then 0.645 is a little bit more than half. Somewhere in this place is the square root of 7. Here, this is negative 10.6, so I have to start at 0. I'll say 0 is there. And then move over a little bit over 10 units to the left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's negative 10. And then keep going a little bit more. That's negative 10.6 right there, approximately. So there you go. We've plotted these two numbers on the number line and classified them for what they are. Let's look at the next two. Now, like I said, 9.3 repeating is 9.33333333. It's got a decimal expansion that has a repeating pattern. Because it has a decimal expansion that has a repeating pattern, we can rewrite it as integer over integer. In this case, technically, the simplest way to rewrite it is 28 over 3. I'm not going to ask you how to rewrite it, but I'm just telling you that that's what it is. Integer divided by integer is 28 over 3. Now, it's not a natural number because we do have a decimal expansion, not a whole number, not an integer, because it has a decimal expansion. It is rational because it can be written as 28 over 3, not irrational, but every number that can be plotted is a real number. And once again, I'll just put 0 somewhere and go a little bit over 9 units to the right. So 9.3 repeating is somewhere over here. It is a positive 9.3 repeating. So there you go on 9.3 repeating. Now 42 is nice. 42 has no decimal expansion, so it is a natural number. And if it's a natural number, then it's also a whole number. And if it's a whole number, then it's also an integer. If it's an integer, then it's also a rational number because we can write it as 42 over 1. It is not irrational because my decimal expansion stops. However, it is real. So it's rational, real, it's an integer, it's a whole number, it's a natural number. 42 is really nice in this sense. Now, there's a number of ways you can graph this. For instance, if I wrote 0 and I moved like 1 unit means 1, that would be tough to do. But you could just mark some spot on our graph as 40, and then each unit could be 1. And then 42 would be obviously right there. So that's one way to graph on a number line, something big like 42, big in comparison to how many tick marks we have. You just start at 40 instead of starting at 0 and then move over 2. Another way to graph is to do a trick where I put, for instance, the 0 here, and then each tick mark is 5 units. So we go 5, 10, 15, 20, 25, 30, 35, 40, And then 42 would be a little bit over 40. So there's 40, but under 45. And that's where 42 is. So that's another way to do it. Instead of making your jumps size 1, make your jump size 5. Or if you made your jump size 10, you could do it even a shorter distance. So a couple ways of plotting 42 on a number line. So that's what I wanted to talk about in in this video. So in this section or this video, specifically the language around natural numbers, whole numbers, integers, rational numbers, and irrational numbers, because we're going to use that language throughout the whole course, and we need to know what those things mean.